Building in space is constrained by extreme thermal budgets and mass limits. When we look at orbital infrastructure, like the International Space Station, we see heavy truss elements held together by methods imported from Earth: bolted joints, fusion welding, and additive manufacturing. All of these require significant power draw, localized heating, or extensive human and robotic labor. But the vacuum of space provides unique physical conditions. When two pieces of clean, oxide-free metal make contact in a vacuum, they undergo cold welding, the spontaneous solid-state bonding of their atomic structures without any applied heat. The two pieces become indistinguishable from a single bulk crystal. For decades, aerospace engineering has treated this phenomenon exclusively as a catastrophic failure mode. Unlubricated moving joints, hold-down points, and deployment mechanisms have seized in orbit when polished surfaces inadvertently fused under load and vibration. We are examining a theoretical framework by Edel Margolin that inverts this perspective. Margolin proposes utilizing solid-state joining as a controlled, pressure-gated assembly mechanism. By shifting the engineering logic from keeping metals apart to allowing them to touch only in geometrically programmed ways, we can design massive, scalable structures that essentially assemble themselves. The first pillar of this framework is the topological cold weld lattice. Instead of flat plates that weld unpredictably, contact surfaces are engineered as three-dimensional interlocking mazes. The second pillar integrates biology. Clean metallic bonds are isolated to the highest points of the maze, while the deep grooves between them are filled with extremely resilient, extremotolerant organic interlayers. This relies on passive geometry. Unlike additive manufacturing, there are no high-temperature electric arcs, no lasers, and no molten metal pools. To evaluate the validity of this theory, we will break down the mathematics of the framework's primary worked example, a pressurized spherical structural module. This system requires no free energy or exotic physics to function. It operates entirely on the calculated interplay of structural geometry and internal pressure. The base module is a 1-meter spherical pressure vessel, constructed with a 5-millimeter thick aluminum-lithium alloy shell. Across the outer surface of the sphere, 12 discrete contact patches form a dodecahedral layout. This maps a single contact patch, a precise maze of raised ridges and grooves. Unpressurized, the gap remains open and fragmented, preventing welding. However, topological analysis reveals 5 independent loops capable of forming continuous welded paths across the entire interface. This topological maze ensures that modules remain entirely reconfigurable during loose handling. They only lock together when a specific mechanical trigger is activated. The trigger is internal module pressure. Elevating the internal pressure to 0.1 megapascals, about 1 Earth atmosphere, generates roughly 1,000 newtons of normal force on each patch. The load concentrates exclusively on the ridge tips, spiking contact pressures to 10 megapascals. This induces plastic deformation. As the metal crushes together, breaking through native oxide films, 3 of the 5 topological loops close, forming a redundant, continuous weld. To guarantee this connection, the alignment mechanism applies a programmed micro-twist, topological fretting. It mechanically scrapes the ridge tips, exposing fresh metal. The resulting shear capacity of the bonded region is approximately 18,000 newtons per module. This geometry-programmed weld provides a safety factor orders of magnitude higher than the low G-forces experienced during station-keeping maneuvers. Cold welding strictly requires a clean, oxide-free metallic interface. Introducing an organic biological layer to the joint seems like it would immediately contaminate the weld. Through strict spatial separation, pure metallic bonding is confined to the ridge tips, leaving cavernous voids between them. These grooves house a porous matrix embedded with dormant spores. This layer provides immediate viscoelastic damping, absorbing kinetic energy and reducing local stress. The physical structure of the biolayer acts as a passive engineering component to manage launch and operational fatigue. The organisms selected for this layer are distinct extremotolerant species, such as the radiation-resistant bacterium Bacillus subtilis or the Antarctic black fungus Cryomoges antarcticus. These spores remain dormant in the vacuum for years. They activate through a targeted micro-injection of water during a scheduled maintenance window. Once hydrated, the spores germinate over a matter of hours, expanding to form a dense biofilm within the groove network over several days. The engineering output of this biological activity is uriolysis-driven carbonate precipitation. The biofilm acts as a template to grow mineral cement directly inside the joint. As the structure flexes and sustains microdamage, this mineral precipitation actively seals microcracks and manages flaws at the cellular level, requiring no external robotic repair. This framework employs biology as a robust, self-deploying sealant, ensuring structural resilience long after the initial assembly. Every joint in the system functions as a capacity carrier, a node that stores and processes structural configuration data over space and time. Looking at this matrix comparing joining methods, we define the first metric as spatial capacity. This is the structural redundancy and load path diversity provided by the multiple, independent weld loops spanning the metal topological maze. The second metric is temporal capacity. This represents the joint's ability to heal microfractures, manage moisture, and resist fatigue over time, driven entirely by the biolayer. Traditional bolted joints or chemical adhesives possess inherently low spatial and temporal capacity. They rely on single-point stress paths and inevitably drift into degraded, brittle states under continuous loading. By combining topology and time as equal variables in the design process, the resulting structure is capable of dynamically processing stress and maintaining its own integrity over decades of operation. To translate this theoretical framework into deployable hardware, the proposed experimental roadmap moves from simple E0 coupon tests in vacuum chambers up to E3 multi-module autonomous assembly demonstrations. A critical hurdle in testing is proving atomic interdiffusion across the joint boundary using XPS and EDS spectroscopy. Without evidence of atomic blending, the joint is categorized merely as a mechanical lock, not a true cold weld. Deploying this framework also encounters strict planetary protection regulations. International guidelines heavily restrict introducing living extremophiles near other planetary bodies to prevent biological contamination. While living biofilms are considered acceptable for infrastructure in low Earth orbit, deep space and lunar surfaces require tightly contained or totally inert biomimics. For high-category planetary targets like Mars, the active biolayer must be substituted entirely. Engineers would rely on heat-killed mycelial scaffolds or synthetic polymer networks that mimic the mechanical damping without the biological risk. Validating this logic shifts the scale of assembly from single modules to kilometer-scale arrays, modular tethers, and self-healing habitats. This transition leverages the clean vacuum to create structures that are physically impossible to launch as single units from Earth. The most efficient way to build massive infrastructure in orbit will not rely on fighting the harsh vacuum with high-energy heat. It will rely on highly specific geometry and biology that use the vacuum to build themselves.